Good morning, good afternoon, and good evening. As Fernand said, my name is Jim He, and I am an application engineer in MSc. Thanks all for attending this webinar. Today, I would like to talk about enhancing safety and reliability of packet seals with innovative marc nonlinear capabilities. Here is today's agenda. First, I will talk about the applications of elastomers in oil and gas industry. In fact, today's topic is also applicable to all the sealing products in other industries. Due to the tough operation conditions of packet seals in the oil and gas industry, it imposes more challenges in the design and simulations compared to other industries. I will talk about how MSc Marc tackles these challenges with advanced features. And at the end, I will show you an example and do a demo. Most elastomers usage in the industry falls into two general categories, compliant and energized. Compliant seals are designed to fit to a predetermined sealing configuration. Examples include O-rings, V-packing, and swap cups. The interference between the seal and the adjacent component ensures that an initial seal is made. On the other hand, energized sealing is formed by applying an external force to cause distortion of the seals. This distortion supplies the interference between the seal and the surrounding structure to achieve the desired sealing. Examples for this type of sealing include pipe rams and packers. A different way to look at this categorization is by looking at the dominant mode of deformation. In compliant seals, the deformation of the material is dominantly deviatoric, while in the energized seals, volumetric deformation plays a critical role as well. Let's look at the three major categories of packers that are critical to valve completion. They are inflatable packers, annular packers or blowout preventers, and downhole packers. The inflatable packers are sent downhole, often through small restrictions, and then inflated hydraulically to the casing wall or open hole diameter to seal up the valve. The strains experienced by the material could be of the order of 500%. Some of the largest rubber parts for drilling and production are annular packers for blowout prevention. Some of the larger rubber parts can be over 1,000 pounds for just a single part. The rubber is bonded to large metal inserts, which provide support and extrusion resistance. Lastly, the downhole packers seal up the region between the casing and production tubing, helping prevent flow of corrosive fluids upstream, and also help minimize tube movement and thus preventing damage. In addition to the demanding performance expected of packers by way of loading and deformation, they are also subjected to extreme environmental conditions. This includes corrosive fluids, high temperatures, and high pressures. And here are the three major challenges when we simulate packet seals with elastomers. First, unlike metal materials, usually there is no published material properties or FEA simulations available for rubber materials. Also, the rubber material properties are obtained by choosing a constitutive model with curved fitting. It actually highly depends on the user's experience and preferences. If you want to take into account for viscosity, temperature, and damage effects, obtaining these material parameters is even more challenging. Second, rubber materials can undergo extremely large deformations, and it poses big challenges for FEA simulations. Element distortions due to large deformation can cause the simulation to stop, even when the loading level is small. Also, since the rubber material is nearly incompressible, it requires development of special element types. Last, seals are in touch with other parts in surfaces, and it can also touch itself. So at different stages of the installation or services, the surface area in touch can also be different. The solver should be able to handle this situation. MSC-marc is a software package that excels in highly nonlinear simulations, including seals. Here are a list of advantages marc provides in terms of rubber simulations. We will talk about these items in details with the following slides. Marc provides many material models for rubber, including the popular Moody, Rivlin, Ogden, and Arruda Boyce models. The user can also define his or her own material model by using user routines. Marc also allows the user to include anisotropic behavior, time dependency, temperature dependency, frequency dependency, and damage effects. For frequency dependency, the material properties can even be dependent on the response amplitudes, which is the so-called pain effect. Marc provides a neat interface to help us to select and determine the material properties for rubber using curve fitting. The user can conduct the necessary material tests and import the test data into the graphical user interface. Then the user can select the material type and do the curve fitting. Marc shows the test data curves and the curves from material fitting so that the user can determine if the material model is satisfactory or not. For structural analysis, the user can use Marc to conduct static and dynamic analysis. Time-dependent effects such as creep and relaxation can also be included. Marc is also a multi-basis code. The user can run multi-basis simulations such as thermal structural coupled analysis. Marc provides exceptional contact algorithms so that it is very easy to set up a contact analysis. In Marc, the user just needs to define some contact bodies and contact pairs, and then specify if there will be group contact or touching contact for these contact pairs. The contact area will be determined on the fly, so the user does not need to specify the possible contact areas, and no contact elements need to be created. For rubber material undergoing large deformations, if we continue to use the original elements, excessive element distortions will prevent the simulation from completing. Marc provides adaptive remeshing to address this issue. There are two types of remeshing in FEA tools. In the first one, the original elements are split into smaller elements. It is very cost-effective and useful to get better resolutions. This is called local remeshing. In the second method, which is called global remeshing, the domain or the space occupied by the deformed elements are determined by the solver, and the solver uses this domain to create a completely new mesh. All the information such as displacements, material properties, contact, and boundary conditions are mapped from the old mesh to the new mesh. And all these operations are done automatically without user interventions. This slide explains why the local remeshing method cannot help to resolve the element distortion problem. When local remeshing happens, the original elements are split into smaller ones. When element distortion happens, if we use local remeshing, we can see that after the local remeshing, the smaller elements are still distorted. On the other hand, global remeshing creates a completely new mesh, and the new elements are without distortions. Many commercial FEA tools, including marc, has the local remeshing capabilities, but only a few of them have global remeshing. And marc is a forerunner to provide this global remeshing option with the best-in-class capabilities. For global remeshing, marc provides a lot of controls for the user to control the local mesh refinement. In this example, the plastic string is used to guide the mesh size. In areas with large plastic string values, the mesh size is smaller to provide good result resolutions. When there is a crack in the model, we can ask marc to use smaller element size around the crack tip so that more accurate results can be obtained. Global remeshing in marc also provides curvature control so that finer mesh is created in the regions of high curvatures. Recently, marc added a new capability for global remeshing. Now, marc also supports 10-node tetrahedral elements with global remeshing. This slide shows the mesh for a crack propagation problem using the lower order elements and higher order elements. With higher order elements, we can ensure we are getting more accurate results. marc provides many different matrix solvers to offer best performance for different types of scenarios. Also, marc supports parallel computing and GPU. The figure on the right-hand side shows the time saving when we use 2 and 4 CPU cores compared to just using a single CPU. Here we are having a simplified packer design with only a few basic components. The first one is the packer element in the center. The second one is a block on the right-hand side. And the third one is the casing ID. And the fourth one is the casing OD. This is an asymmetric problem. So we are going to solve this problem with 2D asymmetric elements. There are 3 different load cases in this problem. In the first load case, we will move the casing ID up with a small distance to preload the seal. And in the second load case, a displacement to the left is applied to the block so that the seal will be compressed. At the end of this step, the seal will fill the space between the casing in ID and casing OD. In this compression load case, global remeshing is used to resolve the element distortions. Here, the mesh at 5 different loading levels are shown. As can be seen in these figures, all the meshes are having proper element shapes without distortions, thanks to global remeshing. The upper figure in this slide shows the equivalent strain value at the end of this load case without using global remeshing. The lower figure shows the same result with global remeshing. Both plots are using the same color scales. We can see that although the load case can be completed without global remeshing, as shown in the upper figure, large element distortions and penetrations are absorbed in the upper figure. Also, the maximum strain value is 72% higher than the case with global remeshing. This slide is similar to the previous one. It shows the contact status. The yellow color means that the corresponding element edges are in touch with other element edges or other components. It is clear that penetrations exist when global remeshing is not used. In the last load case, a pressure of 5,000 psi is applied to the right-hand side of the seal. Under such high pressure, the seal will be compressed furthermore, and extrusion will happen on the left-hand side. In this slide, it shows the animation of equivalent strain values of the packer seal for all the 3 different load cases. We can clearly see the extrusion on the left-hand side. And here in this slide, the animation shows the contact status of the same problem. So this simple packer seal model shows the capabilities of marc with contact analysis and global remeshing. There are many other capabilities in marc that allows the user to run additional analysis. Here are some possibilities. In particular, it is possible to run a 2D axisymmetric analysis first, just like what we have shown, and then map the result of the 2D simulation to a 3D model, then continue with a 3D analysis. Now, it is time for a demo. In this demo, I would like to show you the material model fitting, contact setup, and global remeshing setup. So here, I already created the mesh, and I also have defined 3. What we are showing here are the contact bodies, and I already created 3 contact bodies for these geometric curves. The dotted lines here are showing the orientation of these curves. So as you can see, the packer here is in gray color, which means we haven't defined any contact bodies for it yet. In order to create a contact body for it, we need to we can say create a new meshed or deformable body and add the elements, and we can select all the elements in this model. Of course, we can also change the name of this contact body. And actually, let me delete this guy. And actually, there is a quicker way to do that. We can just say detect mesh body, and marc will automatically determine the groups of elements that are connected together. To explain this concept, I'm going to use another model here. As you can see, in this model we have three parts, and if I use, and all these three parts are not belonging to any contact bodies. Now, if I click this detect mesh bodies, you can see that all three bodies, all the contact bodies are created automatically. Now, going back to my original model here, again, I can change the name of the contact body. Then I can create a contact table to define the contact body, contact pairs. As you can see, the packer can touch itself, and it can also touch all the three different geometric rigid bodies. So, of course, we can define these contact pairs one by one, but even better, we can just click this touching icon here, and then as you can see, all these small boxes have letter T, which means touching contact. And so that's all for setting up the whole contact definition. Now let's move on to the material properties. So in my folder here, I have some material, some files that with material test data. And if I take a look at this, there is something wrong with my editor. But if we look at the file, let me see if I can use another. So it just has two columns. The first column is the strain value, and the second column is the stress value. And we have multiple. In this case, we have three files. They are the test data under different test conditions. So we can say read this data into this marc database. So first, we can select this universal data, and we can say this is from test. So it is experimental data. And okay, and we can also load another one. So same thing here, experimental data. Okay, so now we have two material test curves loaded in the model. What we can do is to go to this material properties, and then there is experimental data fit. As you can see here, it provides material fitting for different types of material behavior. In this case, we are doing just nonlinear elasticity. So we will select uniaxial test data and biaxial test data, and treat this elastomer fitting. In this form, we can choose which element more material model we want to use. Maybe we can use Mooney Griffin, and we can choose if we just want to use a single test curve, or if we want to use all the available test curve. And then we can create this compute. To do the curve fitting. So as you can see here, Marc shows this the uniaxial experimental data, and also the uniaxial from the uniaxial stress strain curve from this Mooney Griffin model. So we can compare these two curves to see if they are good enough or not. And same thing for this yellow color. And also, Marc shows the stress strain curve under other types of loading, such as plane shear and simple shear, so that we can determine if these two curves are reasonable or not. And it also calculates some relative error. And here, it shows the material coefficients for this Mooney Griffin model. If this is good for us, we can just simply say create or apply to create a new material model. And if we double click here, you can see that this material C10 and C01 coefficients have been copied to this material model. Next, let me show you how we can define the global rematching. So we can just go here to say we want, this is a 2D model, so we want to, and we want to use this 2D solid rematching capability. First, we need to select which contact body we want to use as for rematching, and then we can specify, we can tell Marc when the rematching should happen. We can say immediate, the software should rematch, should create a new match immediately, or we can say rematching should happen for every 5 increments. Or even better, we can say we can use this criteria to let Marc to generate a new mesh automatically based on the element distortions or penetrations or other criteria. We can give a global meshing parameters, and also we can define some local requirement here. But in this case, I'm not going to do that. And so that's all for this demo. So in summary, Marc provides a robust and complete solution for packet series analysis, thanks to exceptional material models, great contact algorithm, and global rematching. And that's all for my presentation. And I'm happy to answer any questions you might have.